Okay, good morning.
Good morning.
Let's see. So we talked about semantics in a semantic analysis in a general sense the other day, and today I wanted to go over the three major types. Let's turn that off. Okay, so we stopped here. I think that's true. Denotational, operational, and axiomatic, without discussing in what either one really is. And again, this is giving you just a brief overview. I posted quite a few extra documents on the discussion page. And they go into more detail if you want to have it, but it's not necessary for the course. Do we have questions on the things that we talked about on Monday? Okay. So let's briefly go through these. If you think about what every programming language needs, there's really only 5 program statements, 5 kinds of program statements. Everything can be reduced down to that. The first is you need some kind of a declaration or initialization for variables. The second is assignment, which is slightly different from the first. The first is the one that introduces the memory space into the computer and or introduces a variable name to the program. And the second is, it's always should be considered a reassignment of values. And even if it's the first time that you assign a value to a variable, technically it's a reassignment in the sense that once you declare the variable, that variable exists with an undefined value. So the assignment statement reassigns from undefined to some properly defined value. Every follow-on assignment from that just keeps reassigning the values. So there's 2 of them. Then the third thing you need is some kind of selection, which is the if then else is the standard form. And if you have if then else, you can create all the other forms that exist. You can create switch statements, you can create nested if then else's, you can create if then else ifs. All of those can be replicated with just if then else statements. It doesn't mean it would be pretty code, but they can be replicated. And then you need some form of repetition. So the fourth thing is repetition. And repetition is either iteration, which would be for loops, while loops, all of those variants, or recursion. As you know, there's no difference in computational power between a for loop and a while loop, or a do all and a do while and a for all those different forms. If you have a for loop, you can change it into a while loop. If you have a while loop, you can change it into a for loop. So when people talk about semantics, normally they pare down the software that they're interested in into the basic statements and then start to do analyses on those. The 5th form is IO, but since we're doing analysis on computation and not the input-output per se, a lot of people ignore this when they talk about program semantics. So from that, let's get into the details of denotational, operational, and axiomatic. Denotational describes the program behavior in purely mathematical terms. You can argue that any formalism is a mathematical system, but I mean this in the sense of mathematical expressions, particularly the kind that we're going to study next week when we start to get into lambda calculus. The idea is to abstract away the memory into a notional thing called a program store. And the program store is nothing more than a set of variable value pairs. So if you think about how you initially were taught to think about memory, you were probably initially taught to think about memory in a very concrete physical way as memory space, physical memory space on the computer. And when you say variable x equals 10, then what you're doing is, okay, there's a memory space that is associated with variable x. When you say x equals 10, we're putting 10 physically in that memory space on the computer. And that's great, but then people start to talk about object-oriented programming languages and they say, well, we're not going to worry about the memory space, the physical memory space on the computer so much, we're going to have attribute values. So now it's attribute x 10, and somewhere in memory is this memory space for that object's x attribute. And we're going to put the value 10 there. So there's differences in the programming paradigms. And when you get to functional, which we'll do in a couple weeks, even that goes away and we don't really talk about memory at all. We talk about bindings between variables and values where there's just this magical association between that variable and the value at any point in time. The program store covers all three of those. So this abstraction away from how the memory operates allows the denotational semantics to work across all the different programming paradigms. And the same is going to be true basically for operational and axiomatic. So the store is a set of variable value pairs. That's math model of memory. And I mean set truly in the set theoretical sense. So you can union them, you can difference them, you can do intersections, whatever you need to do with set operations. And the view of what computation is that a program transforms an input store to an output store. Again, when we talk about program meaning, in the larger sense, what does this program mean? Generally, we talk about the observed behavior, observable to an external observer. And what's the observed behavior? I put some input in and some input and some output comes out. So I have an initial store. When I put the data in, that's my initial store. And then when the data comes out, that's the output store. So the idea of what does a program do, what is the meaning of the program, turns into, well, it's something that transforms an input store into an output store. You've probably thought of methods or functions in the same way. If someone says, think of functions as a black box, they take input, they do something, right? They transform that input to an output and then they create output. From there, we can start to make rules for individual statements, but in order to make a rule for the program, I'm going to come back to this one actually in a little bit. In order to make a rule for a program, we have to say, okay, if I have the rules for these 4 individual statements, or 5 if I want to include IO, then that's great, but all I have is rules for statements. I don't have a rule for programs. So then I need to have a rule for how does a program work? Well, a program works one statement after another. And that's true in the imperative world. That's true in the object-oriented world, even though it can get a little more difficult saying what the next statement is. It's not quite true in the functional world, but we can do another form for the functional world when we get to it. So once you have the individual statements defined, and then you have a rule that says, how do I do 2 statements? I do the first one and then I do the second one, and I have a rule for that. Then you have a rule for programs, because once you have a rule for 2 statements, well, you can keep using that rule over and over and over. If a program has 100 statements in it, okay, how do I do statement 2? I do statement 1 and then I do statement 2. How do I do statement 3? I do statement 2 and then I do statement 3. So from there you can expand whatever definitions you have up to the whole program. Only assignment statements can change the store. Think about that for a minute. Does an if then else statement intrinsically change the store? They really don't. Only assignment statements. X equals whatever. How do loops and if then else forms then affect this? Well, the way a loop works is if it has an assignment statement, it will change the store. If it doesn't have an assignment statement, it doesn't change the store. We might make a quibble on loop counter variables, which would be temporarily assigning values to a store simply for the operation of going through the loop. But you may not have a loop assignment value. You may have a while loop that that doesn't have that. Or you may use recursion, which doesn't do that. Same thing with if then else. An if then else statement doesn't intrinsically change the store. Think about if something, then print else, print something else. The store didn't change. The only thing that's going to change in an if then else form is if it contains an assignment statement. So the way you define loops in if then else is basically using this one statement after another rule. Oh, and by the way, if one of the statements happens to be an assignment statement, then it changes the store. Okay, now why do people do this? Well, people like to have formal proofs about program characteristics. Excuse me, again, will it terminate? Will it do this? Will it do that? In particular, people have been using program optimizations for a long time in compilers, and everybody knew they were good. Everybody knew they worked, but for a long time they couldn't prove it. Denotational semantics allowed a proof techniques to come into play to say, okay, now we have provably verifiable, logically sound optimizations. And the basic rule for an optimization, by the way, is you can do anything you like as long as you don't change that input to output behavior. Okay, so since the assignment statement's the only one that can change anything, then let's focus on that. If we have some program store, variable 1 value, variable 2 value, typos, these should be ordered pairs. On and on and on. When you start the program, that's an empty set. And then as you start to declare variables, you're going to add to that. We can define a function evaluate x sigma. So sigma is the store. Evaluate x sigma means evaluate x given the current program store, which is as simple as a lookup, right? Go find x. If it's in the store, then give us the value. If it's not in the store, return undefined. And then we can expand this evaluation to, okay, evaluate the expression based on the current store. Oh, okay, so if an expression is 2 times y plus z, what does that mean? Well, go into the store, find out what the y value is, go into the store, find out what the z value is, and now evaluate that expression based on the current store. And then if we have an assignment statement, and if you think about it, this is the generic form for all assignment statements, right? Some variable equals some expression. I don't care if that expression is a constant, a mathematical equation, a function call, it doesn't matter. Then the common sense notion of what that assignment statement does is take the current value for x, right? X is already in the store with variable value pair, x something. Remove that from the store and then replace it with the x equals whatever evaluation you get from eval expression with the current store. So if we do that a little more formally, we can say, this is take the set of current variable value pairs, remove the current x variable value pair, and union whatever value you get by evaluating the expression with the current store. And so then you add that x variable value pair back into the set. And since it's a set operation, it's a union operation. Intuitively, does what I'm saying make any sense? That if we think of the store as a series or a set of variable value pairings, that assignment statement simply replaces the variable value pairing for the identifier on the left-hand side of the assignment operator. Intuitively, does that make any sense? Or better yet, who thinks it doesn't make sense? That's the person I need to be talking to. Okay, I'm going to take that as silence as acceptance. So now if we have this little program fragment and we look at what the store looks like, we have int xy, and the current store would look like this. X has an undefined value, y has an undefined value. And you say, wait a minute, I know Java. It automatically defines everything as 0. In that case, in that programming language, you would have x0, y0. But for many programming languages, it's truly undefined until you do an initialization. Then we say x equals 10. We add x10 to the store. We remove x undefined. So now our current store is x10. Y is still undefined. Y equals x times 2. We evaluate x times 2 based on the current store. Y is undefined, gets replaced with y equals the evaluation of x times 2 based on the current store. Since x is 10, that's going to be 20. It really is that simple. Oh, I shouldn't say that. I might intimidate someone who was confused about it. Is it clear or confusing?
A little bit confusing.
Okay, what part?
I think for me, more of like the syntax for like different expressions. It's all a little bit new.
Yeah, so again, the one cheap trick that people use in denotational semantics is they say, we know how to evaluate expressions, and we're not going to include that in our definitions because we're interested in program level statements. But let's go through some examples here. Okay, so here's my program store. And then I have I do that. And so I'm going to replace this with the variable value pairings. They're not defined right now, right? I've declared variables, but I haven't given any values for them. I'm going to use U for undefined. So that's my current store. Now I encounter this expression. And all I do is replace this with 25. Because that's what the current binding is. Now, if I said this in terms of memory, if I said, oh, what does this statement do in terms of memory? It sets up memory locations for X, Y, and Z. And what does this statement do in terms of memory? It puts the value 25 in the memory location associated with X. Most people are comfortable with that. But since we are abstracting the physical memory away into this notion of a program store, then all I'm saying is the binding or the association between the variable X now is bound to this value 25. And same trick will happen here. And then I don't know, just making stuff up. So what we're saying now is Z equals evaluate, I'm going to put square brackets there. Evaluate this mess using the current store. Let's move that over here. Well, what is that thing using the current store? If I use y and x and x and x, that's what's y? 16. X is 25. And now once I evaluate that, I'm down to 625 times 2 is 1250. 1250 minus 9 is 1241. And so now my sigma is, oh, I lost my sigma. So as a result of this statement, we're replacing the undefined binding of z undefined. We're replacing that with now the whatever value came out of that expression. Does that help?
Yeah, now I get it. That did help. Thank you.
And I don't care how complex that expression gets, you can do the same trick. Now there are things that are going to be wrinkles. How do you think we could handle a function call? Notice, by the way, I didn't say functions were required in the essential 5 statements. A function call is handled by what's called inlining. You literally replace the function call with the code that the function runs. So that's how we can easily dismiss functions. All we do is replace it with equivalent code in line. And now we have a program that's much longer than it used to be, but it has no function calls. So we can still use these exact same techniques.
How do you handle parameters with those function calls?
You set up just as you would in an actual computer. It sets up local variables. So you declare brand new variables that you use in those lines for the function, and then they never get used again. And you can even, if you want to, remove them from the store if you want to be really precise about it.
Interesting. Thank you.
No problem. Now here's the one that can screw things up. The old increment. Because what does that mean? Don't remember what x plus plus means? It means use the current value of x, but when you're done, increment it by 1. That's what that means, right? Now, by the way, most of us don't do this, or I should say you rarely have an honest to gosh need to do this. But how could I fix that? All I have to do is transform back into my basic sentences. If that means use the current value of x, but then increment the value of x by 1, then I just break it apart into its 2 components sentences. I do exactly what the rule says, and now I can go back to my original rules. And if I did it this way, what does that mean? It means increment x first. So I'll do it that way. But I can go back to my basic rules. So with these basic rules, we can cover all kinds of possibilities. Okay, and then we say, oh, let's go back to this. Let's go back to this thing. Wait a minute, what's this about? We could actually say that a little more formally now. That is, how do I evaluate S2? well, let's see, the evaluation of S1, or I should say the execution, right? To make it distinguished from the evaluation of an expression. How do I execute S2? What is the execution of S1 going to do? S1 takes in an existing store, and then when it's done, there is another store, right? It's a store that potentially changed. And then S2 takes that store and uses that as the current store and does its execution. So once we recognize that basically each statement just passes the store, it may modify it, right? It may change one variable value binding, but it takes the store, passes it to the next statement in the program, passes it to the next statement in the program, passes it to the next statement in the program. The only place where you start to get in trouble here, and it's not a problem with the semantics, it's a problem with programming, is if you have functions that have side effects. And how many of you guys are familiar? I'm going to assume people are not familiar with side effects. I have int x, y, z, and then I say x equals 10 and y equals foo, and then z equals 2 times x. And what's the value of z at this point? Pardon?
20.
Yeah, I like that. Right. Now let's show why that's true and not true at the same time. Let's just make foo the simplest function. Okay, so there, the value of z is 20. Because what does foo do? It takes in nothing and it returns something. Here's what a side effect is. In addition to the function foo doing the job we thought it was going to do, it modifies another variable along the way, and that's called a side effect. And these are generally to be avoided. And the reason is, if I put this x equals 0 in here, without declaring x to be local, therefore it's affecting this x, now it's 0. Oh my gosh, why would you do that? Every now and then there's a legitimate reason for doing that. More often it has to do with large or long-term programs where people are doing program maintenance and they're changing things without realizing that they're stepping on data they shouldn't step on. This is again one of the reasons that the object-oriented paradigm was created, to help encapsulate the data, protect the data. Sometimes people, this is pretty blatant, right? X equals 0. Wow, that's really blatant. What if I used a pointer instead of X? I might be stepping on the X memory space without even knowing it by using a pointer. So that's what side effects are. We can still handle that in the denotational semantics, because we would just inline this code. We would replace this with, instead of y equals foo, I would replace this with y equals 1, and what did I say? X equals 0. And now it's clear from the denotational semantics that, wow, we changed the value of x. From here to here, x got changed. Okay. I'm going to move on to axiomatic and then come back to operational, because operational has a chart in here that can be a little, this chart, this little eye chart that could be a little messy, and I don't want to spend too much time on it. So we'll just run out the clock on that one. Okay, axiomatic. You'll notice I only have one chart here. This is, again, this is the notional behavior, and I gave a one of the links that or PDFs that I gave goes into this in more detail. Chapter, I think it's 11 in the Pelican book that I also gave to you goes into this in much more detail. But this is about the level of detail that we need for the course just to know what they are. Everything is described in terms of true-false propositions, and specifically, they tend to list just the true propositions. These are the things we know to be true of the program at this time. And at any point in time in the program's operation, you have a set of known things that are true. And these are called your preconditions or your pre-statement axioms. And then when you perform the statement, something else is going to be true. And so you can define what these pre and post things are. Now here, they don't worry so much about the program store. However, you can still keep track of the binding because you can say things like this. Is it true that x equals 12 after x has been initialized to 12? That kind of statement can go in there. Now, these are really boring statements. The kind of statements that they really worry about are things like, is x guaranteed to be above 0? Is x guaranteed to be within range of a loop counter variable, or the limits on a for loop? Is x of the right type, of course, is always a question people are asking. These kinds of things. Has x been initialized yet? Those questions. So we have, right off the bat, some set of things we know to be true about the program. What kinds of things would you include? It depends on the question you're asking. Maybe you want to know that all variables were declared and initialized before use. Well, you can add that. Yes, it has been declared. That is a true statement. Yes, it has been initialized. That is a true statement prior to statement S being executed. And then once X is executed, S is executed, then you have other axioms. So again, normally the result of one statement executing is going to have a very small change between your pre and post conditions. Where you get the larger changes, of course, if we think, again, I think we asked this question last week, is an if then else statement one statement or many, And the answer is yes. It is considered one statement, but it is a statement that may contain other statements. So if I had like a loop, right? If S was a loop, which is one statement, but that loop contained other statements, clearly I could have a large change between my pre and my post conditions. One of the things that this is used for, how many of you guys have taken some of the software construction classes where you do talk about, in terms of software design, I want this action to occur, here are my preconditions, here are my post conditions? Or where you talk about software testing in terms of, here are my preconditions, perform this test, here are the post conditions, the intended post conditions. Have you guys encountered this in any software engineering classes?
We looked over it a little bit in SC300.
Okay. Oh yeah. Okay. So as you go on, I think you see it more as you move into SC310, 20, those classes, I think. Was that Oshoa, by the way, teaching it that semester, or was it Schaefer?
Yeah.
Schaefer?
Sorry, no, Ochoa.
Okay. All right. Okay. So that's what I want to spend. I mean, that's really the level that we need to know here. If you get into it, by the way, all of this stuff, it looks like a notational nightmare when you're trying to understand it. So if you go back to thinking just in common sense terms first, it does clarify things. And I'm trying to present this in the most, informal, down to earth way. As an example, I was looking at the Axiomatics handout. Now this is a handout, so they're not really giving you a, so here we are, pre-post, right? The pre and post. And then, but they do talk about a lot more. Oh no, they get into all this operational, you know, they get into this logical if then kind of stuff. Right? So notationally, all this stuff can be rather intimidating. Doesn't that look intimidating? But if you go back to your common sense things, then you can suss all this stuff out. But we don't need to for this class. And aren't you glad? All right, operational semantics, which actually they were writing their axiomatic forms and it looked similar. And the reason is operational semantics, one form of writing operational semantics actually borrows heavily from logic. So I think all of you had to take CS332 to get into this class. And if you remember in your logic, your formal proofs, what did we say? Oh, we have premises and then a conclusion, right? So that's the if-then format used in logic, and it was written as this kind of thing. If I have this, and then a line, and then a bottom, and the things on the top are saying, I have these as premises. I have premise 1 and premise 2 and premise 3. Therefore, I can claim Q. And the way this works in operational semantics is if we have these preconditions, therefore this bottom operation is legitimate. It's called operational semantics because the focus here is on program behavior. And it's either program behavior in terms of the math, like an abstract sense, like how the store is modified or how programs can be constructed, not just syntactically correctly, but semantically correctly. But sometimes people get into operational semantics where they're actually describing hardware operations too. So one good thing about operational semantics, you know, everything is a software, hardware system. You know, ultimately all computational systems are software, hardware systems. So they're combinations, even though, you know, in software engineering, we focus on the software, and in computer engineering, we focus on the hardware. But operational semantics can spread that gap. It can cover both worlds. And so now we can talk about how the software affects the hardware. And once you make that jump, then it goes into, well, wait, the hardware isn't just the chip. The hardware could be a system that the chip is controlling. The hardware could be an air conditioning system that a thermostat is controlling. It's quite widely used. I would say, I'm just going to go out on a limb and say it's the most widely used of the semantics. And the formats are, again, if I have these and I have this and I have this, therefore this is some kind of a valid thing. And the example that I'll use here, and again, this is going to look really intimidating at first until we go into it. Oh, heck, it might look intimidating after, I don't know. This is from the Pelican book. Yeah, come on. Good old there we go. Good old Zoom is in my way. Let's do this. There we go. So in the Pelican book, they use a little tiny programming language that they invented called Wren, W-R-E-N. And Wren is basically an integer-based programming language, I believe, if I remember correctly. And they do that because if you can discuss everything with integers, it works for everything. You know, you can just expand to floats and to strings and all that other stuff. So, and what they do is they define the operational semantics for their entire little language, Wren. And they start out, think of any formal system. What do you have to do? You have to define the things and then define the operations on the things. That's what every formal system does. So they define the things. N is an integer expression, where N is a number. Now they don't define what a valid number is, but we'll assume reasonableness here. ID, that's what they're using instead of var. ID, integer expression. ID is in any legal variable name. any legal identifier. B is a Boolean expression and it has to be true or false, right? Boolean, true or false. And BID is also a Boolean expression and it's a logical Boolean variable name. From those basic things, then they start to make these rules. If I have a Boolean, if BE is a Boolean expression, then not BE is also a Boolean expression. Do you believe that? If you have a Boolean expression, can you put the not operator on it and you still have a Boolean expression? I mean, forget that notation. Do you believe that's true?
Yeah, that seems true.
Yeah, and so what they're doing, if you ignore the notation, what they're saying are very common sense things. If I have a Boolean expression and a Boolean expression, and there's a binary Boolean operator between the two, so Boolean expression, Boolean operator, Boolean expression, I still have a Boolean expression. So what they're saying is, that's what this one is saying. If I have a Boolean expression and another Boolean expression, and I introduce a Boolean operator, then Boolean expression, Boolean operator, Boolean expression is still a Boolean expression. In other words, P and Q, right? If P is a Boolean expression and Q is a Boolean expression, then P and Q is a Boolean expression. They do the same for the integer expressions. If I have an integer and another integer, and then I have an integer operator like plus, that's still an integer operator. So they do these definitions. And again, once you get used to reading this a little bit, it flows pretty easily. Let's see, I have an integer expression and an integer expression, and I have some set of integer operators, which is probably plus, minus, and times, probably, maybe division too. Then what do you know? Integer operator integer is still an integer expression. It's just a larger form of an integer expression. And we kind of knew that, right? I mean, if I said, there we go. It's the difference between $12 is clearly an integer expression. And 12 plus 13 is also an integer expression because it's an integer operator, and an integer. What they're really saying is if you evaluate that, you're going to end up with an integer. Okay, so they make all these rules. And then why do they make all these rules? Well, what they do is they say, okay, we want to know, now this is not quite the same as a syntactic check. They're saying x equals 5, while not x, do x equals x minus 1, write x. We want to know if that's a legitimate command, the command being a program statement. We want to know if that's a legitimate program command. Now, syntactically, they could parse this thing, but what they're doing here is they're actually doing all the type checking. In other words, a legitimate program command not only has to be syntactically correct, but it has to be type correct. And it has to be type correct based on these rules that we have over here. So let me shrink this down a little bit so I can start to not bounce back and forth so much. So we say, okay, well, let's use our rule for how do we get statement sequences. There we go. If I have a command and another command, then command semicolon command is also a command. That's how they get programs out of statements. All they're saying is two commands in sequence is still a command. Now, by command, that's their generic term for, say, a program statement or a string of program statements. So what they want to do is they're asking the question, is x equals 5 while not equals x do write x, is that a command? And now we know, we're looking at that and we're like, of course it is, but you know, if you wanted to do software to to analyze this, you could do that. So what they do is they break it up. They break it up by saying, okay, what is a command? A sequence of commands is a command followed by command is a legitimate command. So as they take the x equals 5 and they break it out over here. And they have a rule that says if we have an integer expression, then an integer ID assignment operator integer expression is a legitimate command. And that rule is, I'm going to shrink this down, and there it is. If we have an integer expression, then an ID assignment operator integer expression is a legal command. So they've determined that x equals 5 is a legal command. Then they take the other two statements, which there's two statements in there, right? While, I'm sorry, there's one statement in there, but it gets broken up. While not x due to the right x. Oh, let's see here. Let's see, here's their while. If you have a Boolean expression in a command, while Boolean expression do command. So now they're going to parse that up, and they get while not equals 0 do equals, okay, they believe that's a command. So they break out the while and they break out the right x, why? Because that's the command, right? That's the command C, is just print x, right x. Are you allowed to do that? X equals right x. Oh, they have a rule for that. If you have an integer expression, you are allowed to say write the integer expression. That's a legal command. So now they've verified that x equals 5 is a command. They verified that right x is a command. They just have to figure out if this while stuff is a command. Oh, I'm sorry, they only write x the one time. The statement inside the while loop is x equals x minus 1. So they start breaking this up. Okay, how can you do that? While Boolean operation do command. Okay, we need a Boolean expression and a command. So there's the Boolean expression, not x equals 0. There's the command, x equals x minus 1. Am I allowed to do x equals x minus 1? Well, let's see. That's going to be, I have an expression and I have an ID equals integer expression. Oh, here's an integer expression. An integer expression is I have an integer and an integer separated by an integer operator. X is an integer, 1 is an operator, negative is an integer operator, therefore that's legal. So basically what they did is they didn't just parse this thing syntactically, they parsed it and showed that all of these data types, if you will, work. Integer expressions, I needed a Boolean expression and I got a Boolean expression. I needed an integer expression and I got an integer expression. So this is not just a syntactically correct statement, it is a semantically correct statement. Now, I'm not going to ask you to parse any of these things, for your homework. I just want you to get the idea of how these things get used. There are different forms of writing operational semantics. This is, I suspect, the most common form. You'll notice when we took that brief look at the axiomatic semantics, they even started framing things this way. Not because they moved into operational semantics, but because it's a handy way of framing things. When we get into, those of you that take SE 410, you will see this form of operational semantics again briefly as part of the proofs of how your systems can be modeled. Oops. Okay. So that is, again, this is a top level view of these three modes. You're almost certainly confused about the details, and that's okay, because you don't need to know the details for the course. Hopefully the questions that I asked are at the same level, but the basic ideas to remember here is denotational is representing things in a mathematical form, as a very direct link to mathematical forms, and they are and this basic operation of adding to and modifying the store. Operational is more of a description of operations via some logical if-then-else forms, at least in the form that we gave. There are different forms, but the overall goal is to describe operations. And these operations can be described as, if you have these conditions, you can perform this operation, or this operation is valid. And axiomatic is in the form of, what do we know to be true about the program at any point in time? And so we have a set of true statements, and then we execute a statement, and then we have another set of true statements: preconditions, statement, postconditions. If you have that basic top level understanding, then that's what I needed you guys to get out of this week. And as I said before, you can take entire courses on this, and entire undergrad and entire grad courses on this kind of stuff. Okay, we're late. I'm going to let you go. On Friday, I have office hours, so we'll do our normal thing. Well, I'll use office hours during this time slot on Friday. If you have confusion, the homework is up now. So if you have confusions, that would be a great time to ask about it. And of course, you can always ask in the discussion section. Good enough? Always good to see you.